So having gathered the basic idea about how to actually cut out slots from a metallic patch, now I will give you a glimpse of the new domain of design of planar microstrip antennas, which I have already mentioned as the fractal design. Now, fractal basically comes from the Greek word fractus, which means broken or splitted or ruptured. Okay. Now, what we will do, we will break the initial dimension of the patch with a particular design motive. What is the design motive? The basic design motive behind using fractal dimensions is enhancement of bandwidth. Now, here I will tell you some basic rules and mechanisms which we usually follow while designing planar antennas. Is that the primary contributor in any planar design, the primary contributor which deals with the bandwidth, which controls the bandwidth of an antenna, is basically the path length of the flow of current. I mean, on this metallic patch that you see in front of you, there will be current flowing on this structure. Only then the radiation can there be. So what is the total length of the current that is flowing on this patch? That basically defines, or that basically controls the bandwidth. Another concept is there. See, we are performing high frequency applications. I mean, of the order of gigahertz, we are doing 10 to the power 9 hertz. Very high frequency applications. Under those situations, the current is concentrated only on the peripheral edges of the structure. The current can only be concentrated on the peripheral edges of the structure. Okay. Now imagine, for the time being, I will just hide this subtraction operation to show you something. So I will also show you how to hide it. See, keeping it under modeling, if you click on this history list, all the operations which you have done, that will be displayed like this. Total 18 operations we have done till now, since the beginning of this structure. This is the Boolean subtraction. Now I will hide it, hide and unhide, both from the same tab. So if you hide it, see, it is hidden. Now close. Structure is modified. Yes, I want to modify the structure. See, now we have come back to the same thing. Now this is our initial structure. Okay, complete square patch. Now I mentioned to you that for high frequency applications, the current is mostly, in fact, very much concentrated on the peripheral edges. So if the current starts from here and has to move around this patch, what is the total length which the current will travel? See, 30 here, 30 here, approximately 30 here and 30 here. So 120 millimeter approximately. That will give us a particular bandwidth. Now I am drawing a one-to-one correlation that if you want to increase the bandwidth, you have to increase the path length of this current, which is popularly known as the electrical path length of the surface current. Electrical path length of the surface current. Okay. Now there is a problem in this. The problem is, if you want to enhance the bandwidth progressively, continuously, from the knowledge that we have developed till now, it seems that we have to increase the path length. How can we increase the path length? By increasing the dimensions of the antenna. Now see, we can't increase the dimensions of the antenna indefinitely, because our first design motive was we want to prepare a compact structure. Compact means small structure, electrically small structure. So keeping that design motive in mind, we can't actually increase the structure. I mean, we can't actually make the structure too large. But at the same time, we have to do that. We wish to do that to increase the path length for the current so that we can have an enhancement of the bandwidth. So these two requirements are basically contradicting. Now imagine we are actually cutting out this slot. Okay. So hopefully you have understood that how this 120 millimeter is coming. 30 side each side. So total 120 millimeter. Now suppose we have actually cut out this slot. So I will unhide this once again. Unhide, close. Okay. See, again the slot appears. Now suppose this current flows from here to this point, flows from here to here. Previously it was traveling a distance of 30 millimeter. Now what will it do? It will come from here to here to here now, here to here to here, and to here. Why? Because the current can't pass through this dielectric bridge. It has to follow a metallic path only. So this portion is removed. That means the current cannot have the straight line of motion now. Instead, it will follow this loop. This loop is actually a bit larger than the previous straight line dimension because these two steps, this coming down and this going up, these two steps have been added. So this plus this was 30. To this, we have added this and this. So what has happened? The path length for flow of the surface current, that has increased. Exactly what we wanted. But at the same time, have I increased the overall dimension of the antenna? See, the overall dimension of the antenna is intact because the other sides have not changed. The overall dimension of the antenna has been kept intact. So basically, we are enjoying the benefit of both the requirements. We are increasing the path length of the surface current by cutting this slot, and at the same time, we are very much able to maintain the overall dimension of the antenna. So we can have the benefit for both structural compactness, structural miniaturization, as well as enhancing the electrical path length of the current. Enhancing the electrical path length of the current will in turn increase the bandwidth. It should increase the bandwidth. This is the essence of fractal design. See, I have basically broken this upper edge. I have broken this upper edge and bend it like this. So I have basically generated a fractal. Okay. And this is the fundamental design motive behind the use of fractals. Now, there are different types of fractals existing. Among them, the most popular fractal is the Hilbert fractal. Under the name of the discoverer, famous mathematician Hilbert, we have this Hilbert fractal. Similarly, we have some other fractals also, which I think I will be discussing in detail in some other sessions, not in this project. But you need to know the names of these fractals. These are Sierpinski carpet, Sierpinski gasket, Koch fractal, Koch snowflake is there. The cross fractal is there. I mean, you can Google out and see the shapes of these fractals, how they look like. Among them, why this Hilbert fractal is the most used one? Because the Hilbert fractal deals with rectangular edges or vertical or horizontal edges. So it is easier to design. But it does not mean that these rectangular slots, rectangular edges, vertical and horizontal edges are the only option that is there with us. We can have triangular fractals also. We can cut out triangles also. That will give us Sierpinski carpet and Sierpinski gasket. You can Google out and see the structures of them. Similarly, Koch snowflake is a hybrid type of fractal. Neither it is square nor it is triangular. It is a hybrid shaped. Okay, so these are of complex natures. So as for now, we will be concentrating upon generating this Hilbert fractal only. So from a rectangular patch, we will cut out rectangular slots only to generate a Hilbert fractal shape. The first slot we have actually cut out like this, which you see in front of you. Another thing I want to tell you is that, see, it is not a mandate that the slot dimensions will be fixed, that the slot dimensions will be of same value. That means, see this slot dimension here. If I cut out a slot from here only, I can make that slot smaller also, larger also. That depends upon me. That depends upon the designer. In that case, we will not call it a Hilbert fractal, but a modified Hilbert fractal. But one thing we have to maintain, it is actually a mandate. You can't mix and match shapes. That means, if first you are cutting out a rectangular slot, then you can't cut out a circular slot like this. Just follow the movement of the cursor. You can't cut out a circular slot like this and claim that to be a fractal. It is a design. I mean, any design you want you can make, but you can't call that a fractal. Because fractal states that the fractal geometry, the laws of fractal geometry states that whatever shape you are initiating, that is known as an initiator, fractal initiator. For example, in our design, this rectangular slot is a fractal initiator, first level of design modification. And each such level of design modification is called an iteration. Iteration means repetitive similar phases, repetitive similar stages. That is known as iteration. So if you perform different iterations, you can't change the shape. If you start off with a rectangle, you have to proceed with rectangular slots only. If you start off with triangles, you have to proceed with triangular slots only. You can't mix and match. That is basically mandate. You can change the dimensions, but you cannot change the shape. Okay. So this we will follow in our design. So likewise, since we have cut out a slot from this upper end, we can cut out slots from this right side also, this left side also, but not from the bottom, because we are actually having this feed line connected to the bottom edge of the patch. If you cut out portion of the patch from the bottom end, then the feed line will actually lose the connection, because this feed line is basically fused with this metallic patch. If you cut out the patch from this bottom end, then with what will the feed line be connected with? Okay, so we don't cut out slots from the portion of the patch where the feed line is connected. In this case, the feed line is connected in the bottom portion. We won't cut out slots from the bottom portion. Now let us similarly cut out slot from this right side. So what should be the first step? The first step should be select this extrude as we have done. Extrude, escape. Extrude profile comes. Now let us give the name slot 2 or slot right, so that we don't confuse. Okay. Same logic, orientation will be Z only because we are cutting out from the same patch only. Okay. Z min should be 1.6 and Z max should be 002. Now one thing I want to alert you people, that these dimensions, Z min, height, orientation, the coordinates, they should be very, very precisely mentioned, or else it will just show an error. The extrude, it will not be cut out of the patch and you will not be able to understand where you have made the mistake. So it is better to take time, don't rush, take time and design, give the design parameters accordingly. Here also no need of giving any values to this twist and taper, because we are cutting out vertical and horizontal slots only. So we won't hamper them, we won't disturb them. Come to this points table. Now let us select this particular point. For our benefit, I will just close this window once. I will select this so that this wireframe type of structure comes. I don't need the substrate, so I won't display it. So select this feed. Extrude, again the same thing. Escape. Slot right. Z bin 1.6, height 0.002. Now see, this point is 15 cross 15. Okay, we will select a point which is here, somewhere here. So for this point, X will be same as the terminal value because we are cutting out a slot starting from this terminal edge only. For this, X will be 15. So let us type 15, put tab, but the Y will not be 15 now. Y will be a bit less because we are not cutting out a slot from this corner. We are cutting out from a lower level. So let us select Y to be 7.5. Okay. Enter. See, this point is selected. Now this point is selected. Now we will come to this point. For this point also, X remains 15 because we are on the same right hand side terminal region, which has the same X coordinate to be 15. Write 15, put tab, but now Y from here has come down by the same value. So if Y for the previous point was 7.5, Y for this point will be minus 7.5 according to the same logic which we have used previously. So Y is minus 7.5. Enter. See, this is selected now. Now we will come inside. If we are coming inside, we are maintaining the same horizontal level. Okay. So Y will remain minus 7.5. But X is not at the terminal region now. X has come inside a bit. So let us select X to be 10. So we will get some point nearby here. And Y maintains its level minus 7.5. Enter. Now from here we will come up. So X remains same because we are at the same horizontal level, same vertical level. So X remains 10. But Y now comes to the first quadrant. So Y becomes positive. So Y will be positive 7.5. So likewise, we have defined 4 points. We should not do anything with the component. We should not do anything with the material because already PEC is selected. We are cutting out PEC only. Let's preview. See, the structure is shown to us. If the structure is shown to us and we are satisfied with it, press OK. Same thing. It is not cut out. It is only demarcated. So what shall we have to do? We have to select the larger one. What is the larger one? This patch. Double click on it. Boolean drop down, subtract. What was the slot, name of the slot that we defined to be cut out? It was the slot right. See, slot right is visible here in the navigation tree. Here. Select slot right. Slot right will be displayed. Press enter. It will cut out. Now, if you compare these two slots now, these two slots are basically having the same dimension. You can make it smaller or larger also. According to design requirements, this can be done. But rectangle will be rectangle only. Okay. So our next design step is that we will generate a slot on the left hand side. Same process. I won't detail this much more. Same process. So we will select this extrude, escape. Now let us name as slot left. Same thing. Z will be highlighted. Z needs to be highlighted. X bin should be 1.6. Height should be 0.002. No need to do anything with twist and taper because of the same reason. Now we will define the points. See, let us select the point here. Now this point is on the second quadrant. So X will be negative, Y will be positive. Let us select X to be minus 15. Minus 15 we have to select because we are considering a point at the extreme left hand side edge where X coordinate is minus 15 only. So minus 15, tab. Now not 15 but somewhat less. So we take the same value, 7.5. Enter. So this point is selected. Next, we will come down. Now we will come down. So minus 15, x remains minus 15. Okay. So minus 15, tab. But this time y has become negative because now we are coming down to the third quadrant here. So y will be minus 7.5. Enter. See, this point is selected. This is selected like an orange line like this. Now we will go inside. So y remains same because we are at the same horizontal level. Y will remain same. So y will remain minus 7.5. But x is now a bit inward. X is not minus 15, but it has come inward. So it will have a lesser value, minus 10, minus 12, something like that. Okay, nearer to the coordinate origin. Let us select minus 10. Y maintains its level, so minus 7.5. Enter. Now we will come up. Coming up means at the same vertical level. So x will remain same. So x remains minus 10. Tab. Now y comes to the second quadrant. Second quadrant y is positive. So we will have 7.5. Now everywhere, before I actually cut out this slot, everywhere you should note one point, that we are following a particular sense of rotation, either clockwise or anti-clockwise. If you mistake here, then the slot will not be demarcated and you will get an error. So be very careful in selecting in which way you will select the coordinate points. Okay. So once you have given these 4 points, again no need to do anything with this component. Nothing needs to be done with the material. Preview. See, again this slot is being shown. Okay. Okay. So again it is demarcated, not cut out actually. So for cutting it out, what shall we do? We will select the larger one. What is the larger one here? The patch. Double click. Boolean. Press the drop down. Subtract. What was the name of the slot that we wish to subtract? It was a slot left. See, slot left is visible in the navigation tree. Select the slot left. It is selected. Press enter. The slot left has been cut out. So we get the final structure like this.